Welcome to this coding walkthrough. In this session, we'll explore the problem Decode the Slanted Ciphertext, number 2075. We'll break it down step by step, analyze the given data, and work through an efficient solution. Let's dive right in. In this problem, we are tasked with decoding a piece of ciphertext that has been encoded using a slanted transposition cipher. To decode it, there's a specific procedure to follow. First, the ciphertext is written into a grid with a fixed number of columns, denoted as n. The characters are placed row by row, starting from the top left corner. If the grid doesn't fill completely, the remaining cells are left blank. Next, the grid is read diagonally, starting from the top left and moving to the bottom right. Each diagonal starts from a cell located in either the first row or the first column, and the characters are read from left to right along these diagonals. Finally, any trailing spaces in the resulting string are removed to produce the decoded plaintext. The input to the problem consists of the encoded text as a string and the number of columns n. The output is the decoded string, which represents the plaintext. Let's look at an example to understand the process better. Consider the input where the ciphertext is CHIEPR, and the number of columns, n, is 3. The first step is to write this text into a grid with 3 columns. When we fill the grid row by row, the result looks like this. The first row contains CH, the second row contains IE, and the third row contains PR. Any empty spaces in the ciphertext remain as blank cells in the grid. Now, to decode the text, we read the grid diagonally. Starting from the top left corner, the first diagonal contains just C. The second diagonal contains H and I, and the next diagonal contains E and P. Finally, the last diagonal contains R. Reading all these diagonals gives us the string cipher, with trailing spaces at the end. The final step is to remove these trailing spaces, giving us the decoded result, cipher. In another example, the ciphertext is "Coding is fun," and the number of columns, n, is 4. Again, we start by writing this text into a grid with 4 columns. The first row contains CODI, the second row contains NG followed by blank spaces, the third row contains IS and F, and the fourth row contains UN with more blank spaces. With the grid prepared, the next step is to read the diagonals to decode the text. Reading the diagonals for this grid, the first diagonal contains C. The second diagonal contains O and N. The third diagonal has D, G, and I. The fourth diagonal contains I, an empty space, and S and U. The fifth diagonal contains F and N. This gives us the string "Coding is fun," with trailing spaces at the end. After removing these spaces, the decoded result is "Coding is fun." Now consider a third example, where the ciphertext is ABCDEFGHIJKLMNOP and the number of columns, n, is 4. Writing this text into a grid with 4 columns results in a complete and evenly filled grid. The first row contains ABCD, the second row contains EFGH, the third row contains IJKL, and the fourth row contains MNOP. Since the grid is completely filled, there are no blank cells. Reading the diagonals here, we find that the first diagonal contains A, the second diagonal contains B and E, the third diagonal contains C, F, and I, and so on. This process continues until all the diagonals are read, resulting in the string ABCDFGHIJKLMNOP. Since there are no trailing spaces in this case, the final decoded result is the same. Additionally, it's important to note that when the grid has empty cells, they must be skipped during diagonal reading. Finally, always remove any trailing spaces in the resulting string before returning the output. To solve the problem of decoding the slanted ciphertext, we considered 2 main approaches. The first is a brute force method based on reconstructing the grid. The intuition here is that the ciphertext is written in a slanted grid with a fixed number of columns, which means we can reverse this process by reconstructing the grid to recover the original plaintext. The steps for this approach include splitting the ciphertext into rows of equal column size and then iterating diagonally through the grid to collect the characters in the correct order. Once we traverse each diagonal, we append the characters to the result and trim any trailing spaces to finalize the decoded message. However, this method has some drawbacks. While the time complexity is proportional to the product of the number of rows and columns, the space complexity can be high because we need to explicitly construct the grid. This extra memory usage can become inefficient, especially when the grid dimensions are large. To address these shortcomings, we also considered an optimized approach that avoids constructing the grid entirely. The optimized decoding approach eliminates the need for a full grid by calculating the character positions directly during the diagonal traversal. Instead of physically constructing rows, we use modular arithmetic to compute the row and column indices for each diagonal. Starting from a specific column, we iterate downward and rightward along each diagonal, appending the relevant characters directly to the result string. Once all diagonals are processed, we trim the trailing spaces to ensure the output matches the expected plaintext format. This approach maintains the same time complexity as the brute force method, but it significantly reduces space usage because we no longer need to store the grid. The trade-off here is that the implementation is slightly more complex due to the arithmetic calculations required to track the indices. Despite this added complexity, the optimized approach is far more memory efficient and better suited for larger inputs, which is why it was selected as the preferred strategy. When comparing the two approaches, the brute force method is simpler to implement and easier to understand, making it a good choice for smaller inputs where memory constraints are less of a concern. However, it becomes less practical for larger inputs due to the memory overhead of constructing the grid. The optimized approach, while slightly more complex in implementation, offers significant advantages in terms of space efficiency. By avoiding explicit grid construction, it is well suited for scenarios where memory usage is critical. Given the constraints of the problem, the optimized approach stands out as the better choice for both performance and scalability. Ultimately, the key insight that enabled this decision was recognizing that the slanted grid structure could be represented implicitly through calculations, allowing us to save memory without compromising on time complexity. This balance of efficiency and practicality makes the optimized approach the ideal solution for this problem. In this problem, we are tasked with decoding a ciphertext that has been written using a slanted grid with a specified number of columns, denoted as n. The ciphertext is created by writing characters row by row, with each new row starting one column to the right of the previous row. Our goal is to reverse this process and reconstruct the original plaintext. To achieve this, we'll use a brute force approach where we first reconstruct the slanted grid and then decode the plaintext from it. Let's begin by understanding how this slanted grid is constructed. For instance, take a plaintext like Hello World and a grid with 3 columns. The first row will contain H, E, and L, followed by the next row starting one position to the right and containing L, O, and W, and so on. This slanted arrangement continues until all characters are placed, with characters wrapping to the next row as necessary. This setup gives us a clear visual representation of how the ciphertext is encoded, which will guide our decoding process. Next, we'll define the input and output requirements for the algorithm. The input to our algorithm consists of the ciphertext, which is the encoded string, and n, the number of columns in the slanted grid. The output is the decoded plaintext string that we aim to reconstruct. The first step in our approach is to initialize the data structures to represent the slanted grid. We use a 2D list, or grid, where each row corresponds to one shifted line of text from the ciphertext. The next step is to calculate the dimensions of the grid. Specifically, we need to determine the number of rows required. This depends on the length of the ciphertext and the column count, n. Since each row starts one column further to the right, we must account for this slant when calculating the grid layout. Once the dimensions are determined, we populate the grid by iterating over the ciphertext and placing each character in the appropriate position. The slanted arrangement is achieved by shifting the starting column for each new row to the right. After the grid is fully populated, the next step is to decode the plaintext by traversing the grid row by row, skipping over any empty cells, and appending the characters to form the final string. The final output of our algorithm is the reconstructed plaintext string. To achieve this, we rely on a few key insights that simplify the decoding process. First, representing the slanted grid as a 2D list allows us to clearly visualize the layout and efficiently perform operations like row-wise traversal. Second, the slanted arrangement is implemented by incrementally shifting the starting column of each row, ensuring that characters are placed in the correct positions. Additionally, we must handle certain edge cases. For example, if the ciphertext is shorter than the number of columns, we need to ensure that no extra rows are created. Similarly, we must account for irregular grids where the last row may have fewer characters than the number of columns. These considerations ensure that our algorithm works correctly for all inputs. The data structures used include a 2D list, which stores the grid with each row as a list of characters, and a string, which is used to construct the decoded plaintext. The 2D list, or grid, acts as the core data structure for this algorithm. It stores the slanted grid, where each row is a list of characters. Any empty positions within the grid are represented by none or an empty string. The string data structure is used to build the final decoded plaintext by appending characters from the grid. Now, let's consider the key operations involved in this algorithm. The first operation is grid construction, where we populate the grid based on the ciphertext and slanted layout. This step has a time complexity of O(m), where m is the length of the ciphertext, and a space complexity of O(r*(n), where r is the number of rows and n is the number of columns. The second key operation is plaintext decoding, where we traverse the grid row by row to extract the characters. This operation also has a time complexity of O(r*(n), as it involves iterating through all cells of the grid. Together, these steps form the basis of our algorithm. Now, let's look at the pseudocode to summarize the entire approach. The pseudocode begins with the function decode_ciphertext, which takes the ciphertext string and the number of columns, n, as inputs. First, we initialize an empty 2D list called grid to store the slanted grid. Next, we calculate the number of rows required. This is determined by dividing the length of the ciphertext, m, by the number of columns, n, and rounding up to account for any partial rows. Once the grid dimensions are established, we populate the grid by iterating over the rows. For each row, we create a list of n empty slots and determine the starting column based on the row index to account for the slant. We then fill the row with characters from the ciphertext, ensuring that characters wrap to the next row when necessary. After constructing the grid, we decode the plaintext by traversing the grid row by row. For each character in the row, we check if it is non-empty, and if so, append it to a result list. Finally, we concatenate the result list into a single string and return it as the decoded plaintext. To illustrate the algorithm, let's walk through an example. Suppose the input ciphertext is Hello World, and the grid has 3 columns. First, we construct the slanted grid. The first row contains H, E, and L. The second row starts one column to the right and contains L, O, and W. The third row starts 2 columns to the right and contains O and R, while the fourth row starts 3 columns to the right and contains the final character, D. Once the grid is constructed, we decode the plaintext by reading characters row by row. Starting from the top left corner, we traverse each row and append characters to form the final result. Skipping over empty cells, the decoded plaintext is Hello World. This example demonstrates how the slanted grid and traversal steps come together to solve the problem efficiently. This implementation solves LeetCode problem number 2075, Decode the Slanted Ciphertext, by reconstructing the original plaintext from the encoded slanted ciphertext. Here's a detailed explanation. 1. Input validation. The method begins by checking if rows is 0 or encoded text is empty. If either condition is true, it immediately returns an empty string since there is nothing to decode. 2. Grid reconstruction. The number of columns, cols, in the grid is calculated by dividing the total length of encoded text by rows. The grid is recreated row by slicing the encoded text into segments of length cols. 3. Diagonal traversal. The text is decoded by traversing the grid diagonally, starting from each column in the first row. For each starting column index, start_col. A nested loop iterates diagonally through the grid by incrementing the row index, I, and column index, j, simultaneously. Characters are appended to the decoded list during traversal. 4. Final cleanup. After collecting all characters from the diagonal traversal, the decoded list is joined into a string. The restrip method removes trailing spaces from the resulting string, as they are not part of the original plaintext. 5. Output. The method returns the cleaned up plaintext string as the final output. This solution efficiently reconstructs the plaintext with a time complexity of approximately O(n), where n is the length of the encoded text. The diagonal traversal ensures all characters are correctly decoded, and the use of restrip ensures the output is properly formatted without trailing spaces. To solve the problem of decoding the slanted ciphertext, we start by checking some basic edge cases. If the number of rows is 0, or if the encoded text is null or empty, we immediately return an empty string, as there's nothing to decode. Next, we calculate the number of columns in the grid by dividing the length of the encoded text by the number of rows. This gives us the structure of the grid. We then initialize an array of string builder objects, where each element represents a row in the grid. Using a loop, we reconstruct the grid by slicing the encoded text into segments corresponding to each row. For instance, for row I, we extract the substring starting at I*calls and ending at I+1 calls. This recreates the grid row by row. After reconstructing the grid, we initialize a string builder called Decoded, which will store our final decoded text. We then proceed to decode the slanted text using a diagonal traversal. Starting from each column in the first row, we traverse diagonally downwards. During this traversal, we append the characters at the current position to the decoded string builder, and then move to the next row and column in the diagonal direction. This process continues until we either run out of rows or columns. Once the diagonal traversal is complete and we have appended all the relevant characters to the decoded string builder, we may still have trailing spaces at the end of the resulting string. To handle this, we use the strip trailing method, which removes any unnecessary whitespace from the end of the decoded string. Finally, the cleaned up string is returned as the result. This ensures that the output is not only accurate but also properly formatted, giving us the decoded message in its intended form. In this example, we need to decode the slanted ciphertext CHIEPR into its original form, given that it was encoded using 3 rows. To start, we calculate the number of columns. The total length of the encoded text is 20, and dividing by the number of rows, which is 3, gives us 6 columns. Next, we reconstruct the grid by dividing the encoded text into rows of this column length. The first row becomes CHI, the second row is EPR, and the third row is ING. This grid will help us systematically decode the slanted text. The reconstructed grid is displayed as 3 rows, CHI, EPR, and ING. Now we proceed to decode the slanted text by traversing diagonally, starting from each column in the first row. Beginning at column 0, we read C from row 1, column 0, then E from row 2, column 1, and a space from row 3, column 2. This gives us the partial decoded text, C, E. Then at column 1, we read H from row 1, column 1, a space from row 2, column 2, and N from row 3, column 3. Adding these, the decoded text becomes C, E, H, N. Continuing the diagonal traversal, we move to column 2. Here, we read a space from row 1, column 2, P from row 2, column 3, and G from row 3, column 4. Adding these to our decoded text gives C, E, H, N, P, G. This process is repeated for columns 3, 4, and 5, completing the diagonal traversal. Finally, we join all the decoded characters into a single string and remove any trailing spaces. The result is the decoded text cipher. This step-by-step approach ensures we decode the slanted text systematically and accurately. In the second example, we decode the ciphertext ABCDEF using 2 rows. First, we calculate the number of columns by dividing the total length of the text, which is 12, by the number of rows, resulting in 6 columns. Then, we reconstruct the grid by dividing the text into rows of this column length. The grid becomes 2 rows, ABC and DEF. To decode, we traverse diagonally. Starting at column 0, we read A from the first row and D from the second row. From column 1, we read a space and E. From column 2, we read B and F. Combining these diagonally traversed characters gives the decoded text ABCDEF. In the third example, we decode the ciphertext high, which has only 1 row. Since there is just 1 row, the number of columns is equal to the length of the text, which is 5. The grid consists of a single row, high. Since there are no additional rows to traverse diagonally, the decoded text is simply the content of this single row after trimming any trailing spaces. The result is high. This demonstrates how the algorithm naturally simplifies in cases where only one row is involved. In summary, the decoding algorithm follows three main steps: reconstruct the grid based on the number of rows and columns, traverse the grid diagonally to collect the characters in the correct order, and remove any trailing spaces to produce the final decoded text. By breaking the problem into these logical steps, the algorithm ensures that we can accurately decode slanted ciphertexts of varying sizes and configurations. The time complexity of this solution can be analyzed by breaking it into distinct steps. First, we reconstruct the grid from the encoded text. This involves dividing the string into rows based on the specified input dimensions. For each row, we take a slice of the string of length calls. Since there are rows and slicing each row takes O, calls, time, the total time for this step is O, rows * calls. Given that the total number of characters in the grid is n, where n equals rows * calls, this simplifies to O, n. Next, we perform a diagonal traversal. For this, we iterate over each starting column in the first row, traversing diagonally downward until we exit the grid. Each diagonal traversal involves at most min, rows, calls, steps, and since there are calls starting points, the total time here is O, rows * calls. Again, this simplifies to O, n, as rows * calls equals the input size n. In the final step, we join the decoded characters into a single string and trim any trailing spaces. The joining operation takes O, L, where L is the length of the decoded string, and since L is at most n, this step is O, n. Removing trailing spaces also takes O, n. When we combine all three steps, grid reconstruction, diagonal traversal, and joining and trimming, the overall time complexity of the solution remains O, n, where n represents the length of encoded text. Now, considering space complexity, the grid reconstruction step involves storing the grid as a list of strings. Since there are rows strings, each of length calls, the total memory used is O, rows * calls, which equals O, n. Additionally, during the diagonal traversal, we maintain a decoded list to temporarily store characters, and its size is also at most O, n. Finally, the output string is created by joining the characters stored in the decoded list. This requires O, n, space, as the size of the output string is proportional to the length of the input. No other significant memory is used beyond the grid, the decoded list, and the output string. Therefore, the overall space complexity of the algorithm is O, n. To put this into perspective, a naive or brute force approach might involve explicitly constructing all possible diagonal strings and combining them, which would result in a time complexity of O, n squared, due to redundant computations and repeated string concatenations. The optimized approach we've implemented avoids these inefficiencies by directly traversing each diagonal in a single pass, resulting in a linear time complexity of O, n. The best, worst, and average case scenarios all yield the same time complexity of O, n. This is because the algorithm always processes the input string in its entirety, regardless of the specific arrangement of the grid. The proof of this linear complexity lies in the fact that each grid operation, whether slicing rows or traversing diagonally, is proportional to the number of characters in the input. There are no nested loops or operations that scale faster than the size of the input. Similarly, the space complexity remains O, n, because the memory usage, comprising the grid, the decoded list, and the output string, is directly proportional to the size of the input. This makes the solution both time and space efficient, scaling linearly with respect to the input size. One of the most common mistakes in this problem is misinterpreting the grid dimensions. Candidates sometimes assume that the grid is a square, with equal rows and columns, which can lead to incorrect plaintext reconstructions. Always double-check the provided number of columns and calculate the number of rows based on the input length. Another frequent issue is overlooking edge cases. For instance, handling empty strings, very short ciphertexts, or grids where the last row is incomplete is crucial to avoid runtime errors or inaccurate results. Additionally, some variations of the problem introduce padding or filler characters to make the grid rectangular. If you forget to strip these extra characters during the reconstruction, your solution might produce errors. Finally, incorrect indexing is a frequent pitfall. Managing row and column indices properly, especially in zero-based indexing languages, is essential for accurate traversal of the slanted grid. Now, brute force solutions can seem tempting, but they often lead to inefficiencies for larger inputs. While such methods might pass for small grids, they can cause time limit exceeded errors on larger test cases. Instead, aim for a solution with linear or logarithmic time complexity, such as O, n, or O, n log n. Recognizing patterns in traversal is key here. The slanted structure implies a diagonal or zigzag order, so understanding this can help simplify your approach. It's also a good idea to clarify the input and output expectations up front. For example, confirm how padding is handled or the exact format of the ciphertext. This avoids unnecessary confusion. Furthermore, optimizing your solution early can save time during interviews. Skip brute force and look for mathematical patterns or direct indexing to streamline your approach. Finally, don't overlook the importance of discussing edge cases. Scenarios like empty strings, single-row grids, or incomplete rows are great opportunities to demonstrate your ability to anticipate and handle tricky situations. This problem also shares similarities with others that involve grid traversal or string reconstruction. For example, LeetCode 6, zigzag conversion involves reconstructing strings written in a zigzag pattern, which requires careful indexing, much like this problem. Another related problem is LeetCode 54, spiral matrix, which emphasizes traversing a grid in a specific order, although the traversal pattern differs. LeetCode 271, encode and decode strings, deals with systematically encoding and decoding strings, which is similar in concept to grid-based transformations. Finally, LeetCode 418, sentence screen fitting, involves text wrapping within a grid, requiring careful handling of grid dimensions and alignment, making it analogous to the slanted encoding process. Exploring these problems can reinforce your understanding of structured traversal and manipulation techniques. There are also alternative approaches to solving this problem that can be more efficient. One such method is direct index calculation. Instead of reconstructing the entire grid, you can determine the original plaintext based on the position of each character directly. This eliminates memory overhead but requires precise management of indices. Another approach is diagonal traversal optimization. By directly traversing the diagonals, you can avoid explicitly constructing the grid, which can significantly reduce time complexity for larger inputs. However, this approach may feel less intuitive and requires a solid understanding of diagonal patterns. For more complex variations of the problem, such as those involving weighted grids or reconstruction costs, dynamic programming might be necessary. While DP adds complexity to the solution, it allows you to minimize costs effectively in such cases. Each of these methods has its trade-offs, so choose the one that best fits the problem constraints and your coding style. Great job! To summarize, we tackled the decoding of slanted ciphertext by reconstructing the grid and extracting the intended message. We discussed the algorithm, analyzed its efficiency, and highlighted key takeaways. Thanks for watching, and stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!